I welcome all the students to the first lecture of Circuits in Transient State. In this lecture, we are going to study the fundamentals of transients, what are transients and how they are produced in any electrical circuit. And then in this particular lecture, we are going to study about the presence of transients in RL circuits, which is either source free or with source. So first of all, let us understand what is transient. So, for example, if someone slaps you very hard, what will happen? You will tremble with a lot of anger. Your face will be red, and you will be very eager to react, right? So, what will happen that if you are a very sincere man, after some time your anger will go away, and you will come to a steady state. You will understand that you had made some mistake, that's why you got a slap, suppose from your father. So the period after you got a slap and before you become steady again or calm again, that period when you were trembling, when you were vibrating with anger, that period is called your transient period. So similar thing happens in an electrical circuit. For example, if you see this first circuit here, there is a switch. This switch is suddenly closed uh, with a voltage source V, which will be connected exactly at time t is equal to 0 with a series combination of resistance and inductance. So what will happen? Suddenly you close the switch, suddenly a voltage is going to appear across the combination of resistance and inductance, and so a voltage will start to appear across inductance. But since the current in this circuit, I is not directly proportional to the voltage, but it is basically depending on the differential of this particular current with respect to time. This voltage VL across this inductor L is actually dependent on the current in the differential form. That's why there will be a factor of time which will be creating some differences in this particular circuit. So this factor of time, how will it affect the state of a particular circuit, the state of current or voltage in a circuit? This we are going to see in this particular part. So earlier in the steady state analysis, what we had assumed that the circuit has already gone into steady state. So in the analysis previous to this chapter, in all the AC analysis and all the analysis, we were assuming that our circuit was in a steady state when we were using this inductor and capacitor circuits. So here in this case, if you see exactly at time is equal to 0 minus, when the switch was exactly not open, just before the switch was closed, what was the current flowing in this circuit? Definitely I at let me write it this way. At t is equal to 0 minus, our current I was 0. Now, since from here, this is your equation 1. So from here we can rewrite it as di is equal to VL upon L into dt. So what is di and dt? Dt is nothing but a very small change in time. And what is di? Very small change in current. So from this equation, you can say that the change in current is somehow dependent on the change in time. So if the time change is very, very small, infinitely small, it is almost equal to 0. So in that case, the change in current should also be 0. So from here, we are getting a very interesting idea that if in any circuit, when there is an inductor, it will not allow sudden change of current. So sudden change means if you are having very small time uh, before a time t is equal to 0, just before, or time t is equal to 0 minus, if the current is 0, then exactly after the switch is closed, which is time t is equal to 0 plus, exactly after the switch is closed, in that case also your current I should be equal to 0, because it should not have any change, because the dt is very, very small, which is equal to almost 0. So right after you switch on the switch, the current which will be flowing in this inductive circuit is going to be 0, because it was earlier 0. So from here you can say that An inductor does not allow sudden change of current. This is very important. You can write it down that the inductor does not allow sudden change in current. Now coming back to the first equation, if we are reached in a steady state, which means there is a lot of time passed after the switch is closed, what will happen? You can assume this dt as almost as infinity. For a steady state, even if it is not infinity, since the circuit goes through a very fast transitions, even some particular constant amount of time can be considered as a steady state or infinite time. So with respect to changes in current. So for a steady state, after a steady state has been reached in this circuit, so in that case, we can assume that this dt is almost infinity. And in that case, what is going to be your value of VL? If this is infinity, this whole thing will be equal to 0. So your VL will be equal to 0. So at t is equal to infinity, which means steady state, I'm writing it as SS, our VL is equal to 0. So VL is equal to 0 means the voltage across this inductor is going to be 0, which means the inductor will be working as a short circuit. So in this case, your inductor will be short circuit, right? Short circuit SC. So what will happen? What will be the value of current in this circuit when the inductor has been short circuit in the steady state? Since you can see this is a DC voltage source and inductor has been short circuited in steady state, what will happen? The amount of current I will be, in this case will be I is equal to V divided by R. So it will normally be working as a simple resistive circuit after the steady state has been reached. So now coming back to the second circuit, here as you can see, the switch was already closed before the time t is equal to 0. The switch was already closed of this RL circuit with this DC voltage source V. So what will happen? There will be a current, and obviously since before t is equal to 0, the circuit would have been in steady state because it was connected for a long time in that for times less than t is equal to 0. The steady state would have occurred, and the value of current I would have been I is equal to V by R. And obviously since the steady state was there, VL would have been equal to 0. So as soon as we move the circuit from this A position to this B position, if the switch is moved from this to this position, how will your circuit look like? It will look like this. Now your circuit has become a source-free circuit, but as you know, there was a current I flowing in that circuit. And as we have discussed right here, that for a very small change in time, there is not going to be a significant change in the current also for a circuit which is inductive. So for t is equal to 0 minus, your current I was how much? V by R. So what will happen for t is equal to 0 plus? Your current is again going to be V by R, because inductor does not allow sudden change in current. So if the current was flowing in this direction, and remember when the current was flowing, the VR value was like this. The voltage drop across resistor was like this, and even the voltage drop across inductor would have been like this, VL, right? This is how the voltage drop from high to low. So what will happen is, in this particular circuit, if you see, since by the rule, the inductor does not allow sudden change in current, which means after time t is equal to 0 for some transient time period, the current I will continue to flow in this direction, because inductor does not allow sudden changes in current, which means the voltage drop across VR is going to be like this VR. But since there is no source in this circuit, and if you want your current to be flowing in this direction, that means this voltage drop across inductor would have to be reversed, and its value will be L. So now this inductor is basically working as a voltage source for this small transient period of time. So what will happen? This inductor will be supplying current, and right after the switch is moved from A position to B position, the same current I will be flowing in the circuit whose value is V by R. But what will happen is, this current will gradually decrease. Why will it decrease? Because the current is flowing through the resistor, and the power will be dissipated in the form of heat because there is a resistor. So the current will gradually go down and it will go down to zero. So finally at t is equal to infinity, what is going to happen, since there is no independent voltage source in this circuit, the energy which was stored in this inductor will gradually decrease and it will decrease to zero. So at time t is equal to zero, your I is going to be zero, right? Now, if we talk about the RC circuit in this third example, whatever we talked for current is going to be happening for voltage across this capacitor C. So let us call this as VC, and the current across current through this capacitor is, let me call it as IC. So we know that IC is equal to C dVC upon dt for a capacitor. So this particular switch S is going to close exactly at time t is equal to 0. So before this switch is closed, what is the value of voltage VC? I will assume that this capacitor is not initially charged. So at t is equal to 0 minus, our VC is going to be 0. So if you talk from this equation 1, if we rearrange it like this, let us call it as dVC is equal to IC upon C dt. So similar to this equation, here you see that if this dt time is very small, this dVC or change in VC is going to be very small. So similar to the inductor case, if at t is equal to 0 minus, your VC is 0, at t is equal to 0 plus, means right after the switch is closed, definitely your VC is going to be 0. So what you infer from this? You infer that a capacitor does not allow sudden change of voltage across it. Similar to the inductor, where it does not allow sudden change of current through it, the capacitor does not allow sudden change of voltage across it. So similarly, at a steady state, what will happen? What will happen is that from equation 1, if you see that if you put this thing as infinity, your IC will become 0. And if IC is 0, what does it mean? If this current through this particular circuit is 0, it means the circuit is open circuited, right? So circuit is open circuited means your IC current is 0 and your new circuit will look like this. This is your circuit which is closed, and after a particular time your capacitor is working as open circuit, and this is your voltage source V. So what will happen is this whole voltage will be appearing across this open circuit, right? You already know it. So your voltage will be appearing across like this. So VC will be equal to V. So at time t is equal to infinity, VC will become equal to V in steady state. So let me revise everything again very fast. In the initial conditions, when the switch is closed, the inductor does not allow sudden change in current. And in the case of capacitor, the capacitor does not allow sudden change of voltage. In the steady state, if the inductor is applied across a DC source, what is going to happen is it will be having as a short circuit. The inductor will behave as a short circuit, and the voltage across the inductor will be equal to 0. Similarly, in the steady state, the capacitor behaves as a open circuit, and the voltage across capacitor is going to be equal to the source voltage, right? Now, coming to this particular arrangement, similar to the previous case that we saw, this circuit was initially in steady state, and as you can already say that in steady state, this capacitor would have been behaving as a open circuit. So at t is equal to 0 minus, VC is equal to V, because the circuit was definitely open circuit in steady state. And what will happen at t is equal to 0 plus? Since the capacitor does not allow sudden change in voltage, VC is definitely going to be V again, and your new circuit will be looking like this. So initially when the circuit was like this, your current I was flowing in this direction, and there was VC and there was VR like this. And what will happen is Now, since the voltage across this capacitor is going to be the same, since it does not allow sudden changes in voltage across it, what will happen is, now since the source, this capacitor is working as a source, the current is going to reverse. In the previous case, what was happening? In the inductor case, the current was remaining in the same direction, but the voltage across inductor was reversing. But here what is happening is, the voltage across capacitor is remaining the same, since capacitor does not allow sudden change in voltages, but the current direction is reversed, and that is why the voltage across R is also reversed, right? So this is how it will happen. And definitely, since the resistor is there, the current will cause the heat to be dissipated because of the resistance R. And after some time, uh, when the steady state reached, and we will call it as t is equal to infinity, steady state, your value of Vc is going to be 0. And if Vc is going to be 0, your current I will also be 0. So this is how it functions. Now, can you tell me what will happen if we close or open a circuit in a circuit that has only resistor? Can you tell me what happens? Since the current I and voltage across resistor VR is dependent on this formula, VR is equal to I into R, and there is no time element in this relationship. Is there any dt or something? Can you see? Since there is no time element in this particular relationship, we can say that whenever we switch on or whenever we switch off, whatever will happen is, does not depend on time. So there will be no transients. Since there is no dt in this equation, there will be no transient in a purely resistive circuit. In a purely resistive circuit, there is not going to be any transient. So at t is equal to 0 minus, your I is equal to 0, which means VR is also equal to 0. But at t is equal to 0 plus, since the switch is closed and there is no time element, your I is going to be V divided by R, means VR is going to be I into R. So resistive circuit does not have any transients. Now, I want you to note down a few points which I'm going to tell, and I'm not going to write here because it will take time. So you just write these points if you have not already done it. That transients are present in a circuit if the circuit has some energy storage elements like inductor and capacitor, or the combination of these two, inductor and capacitor. So for transients to happen, the inductor or capacitor or both should be having in the circuit. Number two, there are no transients in any circuit which has only resistance. So pure resistive circuit does not have any transient. Inductor does not allow sudden change of current. And after the steady state has been reached, if the inductor is applied across a DC source, it will be behaving as a short circuit because the voltage across inductor will be equal to 0. Similarly, the capacitor does not allow sudden change of voltage across it. And in the steady state, if the capacitor is applied across DC voltage source, what is going to happen is, the capacitor will be behaving as an open circuit, and the voltage across capacitor will be equal to the source voltage, right? So this is the introduction of transients in the circuit. I hope you understood, and we will now move forward to our transients in RL circuit without source. Now, let us see this particular circuit, which is a source-free RL circuit. But before it was made a source-free circuit, this inductor was charged by this particular setup. So you just ignore this particular part. You just assume that this inductor was previously charged by a voltage source V. So that when you switch on this particular circuit from A position to B position, what you will see that the current I will initially start flow and it will then decrease. And now we are going to see that what will be the method, or what will be the way in which this current is going to decrease, and similarly the voltage across inductor and resistor across them are going to decrease also. So let us analyze this particular circuit and write down the KVL equation. So as I told you previously that when this particular setup happens, the voltage across inductor is reversed, right? So actually what will be happening is this inductor will be supplying current, so its polarity will be like this. But for the simplicity, for the cause of mathematical equations, I am just assuming that this voltage VL has a polarity like this, in similar way as the VR. So anyway, it is going to come negative, so we will not be bothering about it. So let us write the KVL equation for this particular circuit. So we know that VR plus VL is going to be 0. Definitely there is no other voltage drops or source. So what is VR? VR is nothing but IR plus what is VL? VL is L di upon dt is equal to 0. So this I is basically a time variant I, right? Because definitely the I will be changing with time. It will be decreasing, as you can see by common sense. So I'm just writing it as a capital I for the cause of simplicity. And in the end, I will replace this capital I with the IT, right? So um, let us rearrange it and try to find the equation for I. We can say that R upon L into dt. Let me rearrange it first. Sorry. Some student may not understand, so I have to rearrange it. So I can write it as IR is equal to minus L di upon dt. So if I take dt here and take I here and L this side, what we will get is we will get minus R by L into dt is going to be 1 by I into di, right? So this is what we are going to get. Let me divide it here. So from here, let's go to the upside here. And if we take integration of this particular equation from both the sides, what we will get is integration of minus R by L dt is going to be equal to integration of 1 by I di. So what is the integration of 1 by I? It is nothing but log I, and log I will be equal to minus RT upon L. But uh, as you know, this integral will have limits. So let me take this time limit from 0 to particular time t. So what will happen is, since you have closed your switch exactly as at time is equal to 0, so our time starts from 0, and you want to analyze the function of current, the function of IT. So for that, you have to take the upper limit as t. And what is going to be the limit of I? Since the initial current, initially when you just switch from A point to B point, your current was, let me call it, your current was flowing as I naught, initial current. And what would have been the value of I naught? In the steady state, as you already know, this inductor would have been short circuited, and the value of I naught would have been V divided by R. So what was your I naught? I naught was nothing but V divided by R. So at the time t is equal to 0, since the inductor does not allow sudden changes current, your initial current, since this is a current equation, right? Your initial current would have been I naught, and your final current at the time t, your current is going to be IT, right? Since your IT is the function of time. So we can write it down as as its limit as from I naught to IT, and this from 0 to t. So what we are basically going to get is log IT divided by I naught. Since if you minus in the log term, it is going to be a ratio. You already know that, right? Is equal to minus RT upon L. Clear? Now what we are going to do is we are going to take anti-log from both the sides of this particular equation. So if you take anti-log, you are going to get IT is equal to IT divided by, sorry, I naught is going to be e to the power minus RT upon L. Minus e to the power RT upon L. So if we rearrange, we are going to get the equation of IT as I naught e to the power minus RT upon L. So this is going to be the equation of current IT in a RL circuit, which is source free. So initially the inductor was charged and it was left to respond. And what you are going to get a current IT, which will exponentially decrease since there is a negative sign, right? It is going to be exponentially decreasing with time t. And let us draw a graph for it. So if we draw this current IT with time t, we can see that at time t is equal to 0, if you put, let me clear it, it's very dirty now, RT divided by L. So if you put t is equal to 0, what will happen? Your IT will be equal to I naught, because e to the power 0 is nothing but 1. So initially when t is equal to 0, your value of IT is I naught. So since this is t is equal to 0 point, your current will start from I naught and it will exponentially decrease. And you see that mm, for t is equal to, if you put t is equal to infinity, what is going to happen? E to the power minus infinity, which will be 0. So your IT is going to be 0 at infinite time. So at infinite times, in a steady state, what is going to happen is current is going to be 0. So this is called an exponentially decaying function. So this is how a current will decay in a simple source-free RL circuit. Now, what will happen to VR? Since the current is flowing in this direction only, before that, let us apply this value of I naught. Since we know that I naught is V divided by R from here, we already discussed this I naught is V divided by R in the steady state. We can also write this equation of IT as V divided by R e to the power minus RT divided by L. And before we move forward, let us rearrange and write it like this: V divided by R, which is nothing but I naught e to the power minus T upon L upon R. So why did I write it in this term? This quantity L divided by R is called time constant. And it is represented by this particular symbol tau. This is called tau, right? So we are going to discuss about this time constant in detail in the next lecture. But for the time being, we can rewrite this equation as IT is equal to V by R or I naught e to the power minus T divided by tau. So you will see that this tau has a very important relationship with the steady state. After a certain amount of taus or time constant, we will assume that our circuit is in a steady state. So we will study about this in the next lecture. For the time being, let's move forward and find out the value of VR in this particular circuit. So here, as you can see, the VR is nothing but the multiplication of current IT into R. So VR is nothing but R multiplied by IT. So if you take this IT from here, what you will get, VR is nothing but V e to the power minus RT divided by L. So this is the equation of your VR, and how will you represent it in a graph? You can see that initially at time t is equal to 0, this is your VR. It is also a function of time. At time t is equal to 0, your VR was basically equal to V. If you put t is equal to 0, this whole thing is going to be 1. So initially your VR starts from V and it will start decreasing to the infinity towards the 0 value at the time t is equal to infinity. Now in the last, VL, what is VL? VL is nothing but L into dit by dt. So what you will do, you will just differentiate this equation of IT. So you will get VL is equal to L multiplied by V divided by R, which was I naught. And if what will happen if you differentiate e to the power minus RT by L, you will get minus R by L outside into, again, you will get e to the power minus RT by L. I hope you know the basic differential equations, how you will differentiate any function, exponential function to be precise. So what will happen is this R and R will be cancelling out, this L and L will be cancelling out, and you will get VL is equal to minus V e to the power minus RT divided by L. So remember what I told you in the previous slide, that even if I assume this VL to be in this direction, its value is going to be negative with respect to VR, because in this circuit, this VL is behaving as a source. So definitely VL's value is going to be negative to that of VR. So here we can see that VL is minus V to the power minus RT by L. And what was the value of VR? It was plus V into the e to the power minus RT by L. So if you want to draw the VL curve, it will be like this. So it will start from minus V, and what will happen? It will go to zero at infinite time or in the steady state. So this is your graph for VLT, right? So let's move to the next section. Now let us talk about RL circuit with source. In this circuit, you see that there is a source V, and at time t is equal to 0, we are going to switch this on circuit. So what is going to happen at t is equal to 0, this switch will be connected to here, and there will be current IT flowing in this particular circuit. So we are going to calculate the function of IT. As if we try to write the KVL equation for this particular circuit, we are going to have V is equal to IT into R plus definitely L DIT divided by DT. So this is going to be your equation 1, right? If we rearrange it a little bit, we are going to get DIT by DT plus R by L IT is going to equal to V by L. So let me call this as our equation 1. So this is what we are going to get. Now, for a differential equation like this, as you must have already studied in mathematics, we are going to have a solution like this. A differential equation of this kind will have a solution in the form of CF plus PI. CF is your complementary function and PI is your particular integral. So the complementary function CF is nothing but it is called the source free response or the transient response or the forced response of any circuit. So this is basically your source free response, or it is also called a transient response. So for calculating the CF, we will just assume this V by L as 0. So our equation will be DIT by DT plus R by L IT is equal to 0. So this is a simple differential equation. And if you want to solve it, how will its solution will be? IT is going to be some constant A e to the power minus RT by L, as just we have discussed earlier. So we are not going into the value of A, which is the initial value of current IT. Let us leave it for later time. So we will be getting this constant A, and the current IT will be in this form of this exponential, and this is called your complementary function for the solution. Now, what is PI? Particular integral is nothing but the steady state response of any circuit. Particular integral is nothing but the steady state response. So what is going to be the steady state current of this particular circuit? In the steady state, as we already discussed, that the voltage across this inductor is going to be 0. This inductor will be working as a short circuit. So the current flowing in this circuit will be equal to, in a steady state, your I is going to be equal to a constant, which is V divided by R. So your final solution is IT is equal to CF plus PI. So what we are going to get? IT is equal to this constant A e to the power minus RT by L plus V divided by R. So this is going to be our equation number 2. Now, how to calculate the value of this constant A? It is very easy. In this circuit, as you can see, at t is equal to 0 minus, what was the value of your current when the switch was not closed, right? Before the switch was closed, your it was equal to 0. So what will happen at t is equal to 0 or t is equal to 0 plus, your it is going to be 0. So if you put this t as 0, this this whole current should be equal to 0. So you can write it as 0 is equal to a into, since if you put t is equal to 0, this whole thing will become 0 plus v divided by r. So let's go to the next slide. So we will get our equation as 0 is equal to a plus v divided by r. So what is this a? Sorry, what is this 0? 0 is nothing but the initial value of the current, right? What was this? This was the value of current it, which was 0 when we put t is equal to 0 or 0 plus, doesn't matter. So it was the initial value of current. And what was this? This was the particular integral, and this particular integral is basically your final value of current. So final value of current, we can call it as I infinity, because infinity is the steady state time we are assuming already. And this is your, this 0 value is your nothing but your initial value, which is your I 0 plus, right? So in this particular section, we are going to represent initial value as time t is equal to 0 plus, and final value as time t is equal to infinity. So if you see very clearly that this value is your initial value and this value is your final value of current, right? So if you rearrange, you can find the value of a as 0 minus v divided by r, which will finally be v divided by r. So in general term, you are going to get this similar type of equation all the time. So generally, you can write this constant a will be equal to initial value of current minus, oh, sorry, initial is 0 plus, right? Initial value of current minus final value of current. So this is going to be your standard formula for calculating I, right? So if we write this equation, which is equation 2, in the general form, how we can write the equation of IT? We can write it as like this. IT is equal to, what is the value of A we got? Generally, we got A is equal to 0 plus, which is initial value, minus I infinity, which is final value, e to the power minus RT by L, and then what we did, we added particular integral, which is final value of the current, and plus I infinity. So this is going to be your standard equation or standard format for solving any kind of circuit in this particular transient analysis. So even if it is an RL circuit or it is an RC circuit, you are going to find a similar equation. So here in the case of RL circuit, you are getting it for current. In the RC circuit, you will be getting it for voltage, and similar equations will be followed. So just remember, this is the initial value and this is the final value, and the difference of these two is going to be your constant A. Sorry, is going to be your constant A, and this is particular integral, and definitely it is going to be your the final value, right? So just remember this type of standard formula and you are going to easily solve all kind of questions in transients. So coming back to the equation of RL circuit with source, we had got IT is equal to minus V divided by R. This was the value of A, right? This was the value of A, minus V divided by R, e to the power minus RT by L plus V divided by R. This was our equation number 2. This was the current equation. So if I want to draw it, how will the equation look like? Can you tell me how is it going to look? So at time t is equal to 0, if you put this is your IT, this is your T. So at time t is equal to 0, this thing is going to become 1, and you will be getting minus V by R, and here it is plus V by R. So at time t is equal to 0, your current will be starting from here. And at time t is equal to infinity, this thing is going to be 0, since e to the power minus infinity, and you will be getting a value V by R, which is constant. So in the steady state, we are going to get the value of current V by R in the steady state, and there will be a starting current of 0 ampere in this particular circuit, which is obvious because as you can see in the RL circuit, if the switch is suddenly on, initially there was no current and inductor does not allow sudden change in current. So initially the current will start from 0, and as the steady state reaches, you know that the voltage will be, the inductor will be short circuited and current will be V by R. So between this 0 current to the V by R current, there must be a curve through which the current will follow and reach the steady state, and that curve is nothing but an exponential curve, because this e to the power minus RT by L function has arrived. So what will happen? This curve will look like this. It will steadily increase and go towards the steady state at time t is equal to infinity. So this is the curve of your current. So it is kind of a charging. It is charging the particular circuit which is having an inductor. So what will happen to VR? VR is nothing but IT into R. So this whole equation will look like this. It will look like minus V e to the power minus RT by L plus V. So everything is going to be same, just this curve will be looking like this. This steady state will be V, and the curve will be like this, right? So from 0 to 2, the voltage across resistor will be moving towards V. Now, can you tell me what will be happening to the voltage across L? So VL is, as you know, it is L dit by dt. So if you put the value of IT from equation 2 in this particular equation, you are going to get L into d dt of, what is the value? Minus V by R e to the power minus RT by L plus V divided by R. So if you differentiate, definitely you are going to get, this thing will be 0 since this is a constant. So you will get L into minus V by R into minus R by L e to the power minus RT by L. So from here, L will be cancelling out, this R will be cancelling out, and this minus minus will become positive. So you will get VL is equal to V e to the power minus RT by L. So you will get a very simple exponential equation which will start from V and it will exponentially decrease to 0. So if you plot it, this is T, right? If you plot this equation of VL, you will get a value at T is equal to 0. Definitely it will start from V, which is the source voltage, and decrease it to 0 at the steady state. So it is very understandable, because in this circuit, if you see, when the switch is on, since the current was 0, the inductor will initially be working as an open circuit, because it will not allow sudden change of current, and whatever the voltage was in the source here will be appearing across the inductor in the initial condition. So it will start from V and it will then exponentially decrease to 0, because obviously in the steady state the voltage across inductor is 0, right? So this is how the transients work in a RL circuit. So I hope you understand, and we are going to see the transients in RC circuit and a little more about time constant in the second lecture of this video. Thank you.